Okay, welcome. We're going to get started lecturing today on chapter 2. Reminder on that. We are starting the first experiment today, the real sort of experiment, which is experiment 2, which is measurements and stuff like that. And let's see, again, the written pre-lab for Canvas is due today. A reminder that I did extend the send gauge stuff, I think, until I want to say next Monday. I think the first few are due. Again, after next Monday, all the send gauge pre-labs will be due on the day we do the experiment. So I just gave you a little bit of time to kind of get those first couple or get yourself signed up and stuff like that. But so technically speaking, I think next Monday you have kind of 3 of them due pre-labs. The 2 for this week, and obviously 1 for next Monday. And again, that hopefully should give you enough time, if you haven't done so already, kind of get yourself up there on that set gauge stuff. And again, a reminder, as we talked about, there is 2 different set gauge things that you need. Again, one is the pre-lab, and one is the textbook homework. Any questions on any of that stuff? Okay, so we're going to get started with chapter 2, actually. Chapter 1, there's not a lot sort of in it. There are a few slides on the handout, and by the way, the handouts can be found up on Canvas. There are a few slides from chapter 1 involving the scientific method, hypothesis, and stuff like that. So you are responsible for chapter 1. You're technically responsible for the few slides that are in there. There's not a lot going on in chapter 1. So just make sure you do look over the couple of slides there from chapter 1. And we're just going to kind of get into chapter 2 here. All right, so chapter 2, we're going to talk about measurements, and just remind everybody, hear me okay? Okay. So in this chapter, we're going to talk about obviously how to properly take measurements. We're going to talk about things like significant figures, how to record all those things. What's that? You can come in. Are you close? We're going to talk about things like density, conversions, dimensional analysis, and so forth. So let's get started. So one of the really most important things when we do take a measurement are actually units, and units are extremely important. You know, for example, if I just write something like, hey, I got 100, you know, what does that really mean? You know, that could be $100, you know, that could be 100 pickles, you know, these things are very, very different. So it's really important whenever we take a measurement and record something that we not only record the number and the measurement, obviously to the proper number of sort of digits, but then we also record the proper units associated with it. The units give us sort of a idea as to obviously, you know, what that number is referencing. Again, there's a really big difference if you got $100 versus even 100 pennies, right? In terms of the amount of the money and stuff like that. So units are extremely important. They are sadly often left out by people when they are taking measurements, but you should always include units in your measurements. You should also always include units as you're doing calculations. It oftentimes, as we'll talk about, helps you understand maybe what should be canceling out, what should be staying, and all those things. Now, there's really sort of 2 widely used system of units. One is the English system, which is sort of what we use. And then pretty much everybody else uses like the metric system. And obviously, as the world got smaller, that does create a problem. And so obviously, some people are using the English system, some people are using the metric system. You know, that can run into a lot of sort of issues that can occur. So believe it or not, in 1960, they had a conference on weights and measures. Sounds exciting. And they came up together with sort of a common use units that are used in science, specifically in chemistry as well. And those are sometimes referred to as the International System of Units, are a lot of times just abbreviated the SI units. So you oftentimes will see the SI units sort of mentioned a lot in chemistry. And really, the SI units are, for the most part, based off of the metric system. So it's sort of really a metric system base of units. And we oftentimes will use these SI units in chemistry. We do oftentimes, though, in problems kind of cross over between English and sort of metric units as we go through it. So here are the sort of fundamental units, or the SI unit for different types of quantities. And it's really important, and sometimes it happens in chemistry, maybe early on in chemistry. People don't really have an association of sort of what the units for a particular type of quantity is. So when we talk about mass, a lot of times we use kilograms, but grams is another common sort of unit that we see a lot for mass. Length is the meter. Time is the second. And temperature is a unit that you might not be too familiar with yet, but you will be very familiar with as we go through sort of this semester. And that's actually Kelvin. So Kelvin is sort of the unit that we use for temperature pretty much, I would say almost 99% of the time in chemistry. A lot of times, as we'll talk about in this chapter, we convert from something like Celsius, degrees Celsius, to Kelvin. But Kelvin is definitely a very, very common unit of temperature that you see in chemistry. It's a pretty safe bet that you're doing something with temperature in a calculation. You should get it into Kelvin if you want to sort of do the calculation correctly. So let's talk a little bit about some of these common sort of measurements that we see for length, volume, and mass. These are some conversions. For example, these are some equalities. This is an equality here, as we'll talk about a little bit later on in the chapter. An equality basically means that they are two things that represent the same amount of something, but are on different units. So when we talk about 1 meter is equal to 39.37 inches, these basically both represent the same amount of length. And as we'll talk about later, we can kind of use these as conversion factors. Like, for example, 1 meter is 39.37 inches, or 39.37 inches is 1 meter. So we can kind of use these as conversion factors to do it. I would say in terms of length, very common is the meter for sure, centimeter, and really kilometer we come across a lot. Decimeter, not all that much. But those three sort of length measurements are very, very common that we do definitely come across a lot in chemistry. Here are some relationships. 1 centimeter is basically 0.01 meters. 1 kilometer is 1,000 meters. So I would say this conversion here, we do see a lot, and we do use a lot here in chemistry. Also going from centimeters to meters, that's one way that you can do it. Maybe you also know that there are basically 100 centimeters in 1 meter. So that's another sort of relationship that we do use a lot here in chemistry. Any questions on that there? Now, because really the SI unit is based off of sort of the metric system, a lot of times we will use really prefixes, sort of these metric prefixes. And this is a table of some of those prefixes. And it is very, very common that people really use these incorrectly. So, for example, people will look at a table such as this, and they'll go, okay, cool. Mega is 10 to the 6, or that's basically 1 times 10 to the 6 in scientific notation. When you look at a table like this, what this means is, for example, That is how many there are in the base unit to one of the prefix units. So for example, what this would mean is in 1 megagrams, for example, would be 10 to the 6 grams. And it's very common. People will always sort of run these guys backwards and kind of mix them up and do it the opposite way. So they do not go that way. For example, if we had centi here, which is 10 to the minus 2, what that means is in 1 centimeter, there is 10 to the minus 2 meters. Centimeter is the prefix. This is the base unit. So that is a very, very common error that people make all the time. They go to a table like this, they pull that off, and they go with, okay, that's how much there is of the prefix unit to the base unit. And again, it's the opposite of that. And you want to make sure you don't catch yourself in that sort of problem. And again, same idea here. If we had milli, it is 10 to the minus 3. I thought it was a. And again, if we had 1 millimeter, that would equal 10 to the minus 3 meters. By the way, 10 to the minus 3 is really the same thing as 1 times 10 to the minus 3 if you were to put that into, say, scientific notation or something like that. And that's sort of how we get to this guy here. Any questions on sort of the prefixes there? Again, very, very common mistake people make. And we do use these prefixes a lot. Again, I would say definitely kilo we see a lot. Centi, milli we see a lot. Not a lot in this chemistry class, but if you continue on to 1A, micro and nano is something that you see a lot as well. You do see those a lot in, say, 1A. But so I would say for our class, definitely centi, milli, kilo. Those are very common sort of prefixes that really do pop up. Any questions? So here's sort of a conversion, or the difference between, say, English and metric. This is a ruler, by the way. It's good to know. Yes. On the top are inches. On the bottom are centimeters. The little dashes are millimeters. Yes. So 10 millimeters to a centimeter. Yes. Now 1 inch is 2.54 centimeters. That is a conversion that you do come across a lot, and that is one that you should be familiar with. So you definitely should know that 1 inch is 2.54 centimeters. So again, inches up here, centimeters, the big numbers, and millimeters, they're the small little guys or markings that are on a ruler. So let's talk a little bit about volume. Volume is the three-dimensional space that's occupied by a substance. Volume is length cubed. So there's a couple of different ways that we can sort of get a volume. We could very simply just fill, obviously, some type of container or measuring device with it, take a volume reading. Sometimes if we have like a cube or something like this, we can actually take sort of 3 length measurements. If we measure the length times the width times the height, these are all basically length measurements. And if we do that in centimeters all the way across, what we end up getting is what is referred to as a cubic centimeter. A cubic centimeter is actually a volume. So a cubic centimeter is a volume. It is basically 3 length measurements that are taken and multiplied by each other. And we oftentimes can find something like the volume of a cube that way by taking the length times the width of the height. Again, each of these measurements are length measurements. but multiplying them together does give us a volume measurement. Now, centimeters cubed is a very common volume unit that we do use in chemistry. 1 centimeter cubed is the same as a milliliter, as we see here. So a centimeter cube or a cubic centimeter is the same thing as a milliliter. A milliliter and a cubic centimeter are two very common units that we use here in chemistry. By the way, if you're talking more like, I don't want to say healthcare, but sometimes people will actually call a cubic centimeter cc. Like if you're watching any type of medical show, they're giving that guy 5 cc's of this before he dies, right? And that's basically 5 milliliters. So that's a cubic centimeter, sometimes used, in medicine that way. So basically a cubic centimeter written like this, or a milliliter. They're all basically, I won't say the same thing, but they're all basically a one-to-one relationship between each other. They all represent basically the same amount. Liter is also a very common unit that we use here in chemistry. And this relationship right here, 1 liter is 1,000 milliliters. That is something you probably should know as well. You use that a lot in chemistry. A lot of times when we take a volume measurement, a lot of the equipment that we use, we take it in milliliters. And a lot of times in some formulas and stuff like that, we oftentimes have to convert it into liters in order for it to sort of be correct. So that is super, very common conversion. You also can move the decimal place 3 places to the left or right, depending on which way you're going. We'll basically accomplish the same thing. Any questions on that there? So let's talk a little bit about mass. When we so mass is the quantity of matter that's present in objects. So what is matter? Matter is basically anything that basically occupies space and takes up area. So it's pretty much anything. We measure mass on the equipment here, like we will do in lab today. This is what is referred to as a balance. It's sometimes referred to as an analytical balance, that particular one, which is a digital scale, basically. So this is a balance. And this is a digital balance, which means when we look at it and we take the reading, we should always record all the digits that we see. We basically open the sides, put in what we need, and take a reading. Before we do that, we typically will tear the balance to make sure it's zeroed out and kind of open it, put whatever you're trying to measure in, and you'll measure it. Again, some very common sort of units of mass, kilograms and grams and milligrams. I would say all 3 of these guys we do come across a lot here in chemistry. Definitely there is 1,000 grams in a kilogram. That's a very common sort of conversion that we come across a lot. Also that there are 1,000 milligrams in a gram. That's also another very common sort of conversion that we use a lot here in chemistry. Now, there is a difference between really mass and weight, and sometimes people sort of use them interchangeably, but there is actually a difference in sort of the meaning of the two. Weight refers to being really affected by the force of gravity. So weight does take into account sort of the force of gravity. Mass is sort of independent of that. So when we weigh things here in sort of chemistry, we should usually refer to it as the mass. The mass of an object technically would be the same here as, say, on the moon, but the weight of those objects would be different as there's different force of gravity in both locations. So we do refer to it, it's kind of on the process, obviously, that we do. when we do measure something like mass is the process of weighing. So very common people sort of refer to it as weight because of that. But we should refer to it as the mass. And again, weight really does refer to sort of the effect that the gravity has on it. So let's talk a little bit about temperature scales. And there's really three major temperature scales that we do come across in life, I guess. But really in chemistry, as we will see, there's sort of really one that we use a lot. So the three different temperature scales is we have degrees Fahrenheit, or the Fahrenheit scale. Water boils at 212 degrees Fahrenheit and it freezes at 32 degrees Fahrenheit. This is the scale we use, to take our temperature, the weather outside, how cold it was during the Green Bay game, right? When it started snowing, all that kind of stuff. Games this weekend, that's all decided by like a field goal, basically, right? All right. We also have the Celsius scale, which is degrees Celsius. 100 degrees Celsius where water boils, and it freezes at 0 degrees Celsius. And a third temperature scale, which is really the temperature scale that we use the most here in chemistry, is the absolute temperature scale. It was later renamed the Kelvin temperature scale. And water boils at 373 Kelvin and freezes at 273 Kelvin. One important sort of note between the sort of three temperature scales is in Fahrenheit, we do say degrees Fahrenheit. In Celsius, we do say degrees Celsius. In Kelvin, we do not. So no degrees. You don't write there is no degrees Kelvin or anything like that. It is just Kelvin, and that's a major difference between them. I would say probably outside of this chapter, I won't see too much Fahrenheit used in chemistry. You do see a lot of Celsius, and like I said earlier, we do have a lot of Kelvin. A lot of what we do is convert from Celsius to Kelvin is a very common sort of conversion that we do here in chemistry. The sort of differences between sort of how we go from one temperature scale to the next is basically the difference between sort of boiling and freezing on each of them. There's about 180 units on the Fahrenheit scale, while the Celsius and Kelvin scale, there's about 100 sort of units. So taking the difference between the freezing point and the boiling point allows us to sort of get our conversions to go between them. So let's talk about these different conversions here. They are all three in boxes, which makes me think you should know. Yes, they will not be provided for you. So you do need to know how to go between the different temperature scales. And probably the most common one that we'll use is obviously the top one there. As I mentioned before, a lot of temperature measurements that we take in chemistry is done in degrees Celsius. And then we need to convert it to Kelvin. So to do that is the top one here. To convert a temperature into Kelvin, you take basically the temperature in Celsius, which is this, and you add 273 to it. The really correct number is 273.15. Most people leave off the 0.15. If you're fond of the 0.15, you can leave it on. But usually what ends up happening is it gets rounded off anyways. So most people kind of leave it off. But if you see that number, that is really the true conversion, 273.15. Most people just use 273 and call it a day. I personally use just 273. You're good at most places to use just 273. That also means in a case where you need to go from Kelvin back to Celsius, the temperature in Celsius would be the temperature in Kelvin minus 273, obviously. So I would say probably 99 times you'll be doing this conversion here, taking it from Celsius to Kelvin, but sometimes you do need to go back the other way. And obviously you just subtract 273 to the other side. This is a conversion to go from Celsius to Fahrenheit. And to go from Fahrenheit, or to convert to Fahrenheit, it is 1.8 times the temperature in Celsius plus a 32. So 1.8 times the temperature in Celsius plus a 32 gets you your conversion to Fahrenheit if you're starting in Celsius. By the way, the 1.8 is based off of the difference between boiling and freezing. It is also, if you learn maybe when you're younger, a fraction like 9/5, same deal. So 9/5 gets you there as well. If we want our temperature in Celsius, it is this guy. So we would take the temperature in Fahrenheit minus 32 and divide it by 1.8. And that will get you your temperature in Celsius. Like I said before, probably outside of this chapter, probably not going to use too much of these two. This is definitely the one most of the time up here. The Kelvin one we're going to use the most. But you do need to know all three of those things. Any questions on those there? Now, if you if you need to go from Celsius, to Kelvin, or from Fahrenheit to Kelvin, you got to go Fahrenheit to Celsius, Celsius to Kelvin, and vice versa. Obviously, if you're going back and forth. All right, so why don't you take a couple minutes here and try each of these. We want to figure out the temperature. That's 28.5 degrees Celsius. We want to convert it to Kelvin. Then we're going 41 degrees Celsius to Fahrenheit and 160 Fahrenheit there to Celsius. So grab your calculator, take a couple minutes, make sure you know how to do it. I'll do it as well. Okay, let's take a look and kind of see how we're doing. So on the first one here, we're really going from Celsius to Kelvin. So remember that basically our temperature in Kelvin is 273 plus our temperature in Celsius. So really on this one here, we just need to add 273 to it. So our temperature in Kelvin are 28.5 plus our 273. Again, I'm going to leave the 0.15 off there. And gets you 301.5. And again, here it is Kelvin, so no degrees or anything like that. Should just be capital K next to it. Any questions on that there? Now, one thing that's important when we do temperature conversions, and really only when we're talking about just strictly taking a temperature and converting it from one temperature scale to the next, is when we do the conversion, what we want to do is basically make the converted number look like the original number. And what I mean by that is our number that we started with in this particular one was 28.5, went to 1 decimal place. So when I convert it, I want to keep it to 1 decimal place. If I have a temperature that's a whole number, when I do the conversion, I want to convert it to the whole number. And that's just a specific thing for temperature. Basically, you want to make the converted value look like the original value. So if it went to 2 decimal places, you would convert it to 2 decimal places. And it's really because there's a lot of significant figures problems with temperature conversions. Some people use 1.8, some people use 1.80, some people use 9/5. So there's a lot of sort of variations that you could go if you follow sort of strict significant figures like we'll talk about here in just a second. So that's the general rule. Temperature conversion, make the converted number look like the original number, however many decimal places or whole numbers it went to. So here we have Celsius and we want Fahrenheit. So the temperature in Fahrenheit is 1.8. Our temperature in Celsius plus a 32 gives us 1.8 times 41 plus a 32. That is going to get us on our calculator here 105.8 degrees Fahrenheit. And this is a situation where if I look at the original number here, it is a whole number, which means I would want to take this to 106 degrees Fahrenheit. Take it to the nearest whole number, obviously rounding correctly. So that's an example of what I was just talking about. Obviously on the calculator, this is what you get. Following sort of our rules here for temperature conversions, we would look at the original number and see, again, it was a whole number, so we'd want to do the conversion to a whole number. Any questions on that there? Lastly, we're going from Fahrenheit here to Celsius. So temperature in Celsius is the temperature in Fahrenheit minus 32 divided by 1.8. That is going to get us 160 minus 32 divided by 1.8. Like 71, 1111. So again, on your calculator, you basically get like 71.1111 all the way across there. Same deal here. We're going to look at our original number here, which is 160, a whole number. So we would take this to 71 degrees Celsius. Any questions on any of those examples? So again, a reminder that these temperature conversions will not be given to you, so you definitely need to know them by heart. And I would say definitely Celsius and Kelvin you need to know by heart if you plan on continuing on in chemistry, because you use it for like every calculation. Any questions on any of that? Yeah. All right, so let's take a look at each of these just to make sure we understand what type of measurement we're looking at here. So we have 523 Kelvin. Kelvin is a unit of temperature, which means here we are talking about, obviously, temperature in that case. Here, looking at the unit, 25.36, capital L. L is liters. Liters is a unit of volume we're looking at in this particular case. M is meters. Meters is a unit of length. kg is kilograms, and that is a unit of mass. Now you may say, well, seems logical, but I can tell you personally that I've seen a lot of people say things like, I had a volume of 500 grams, right? And that is definitely not a volume. Or, I had a mass of 52 milliliters, so it's really important to understand what the units are, what they represent, so you don't run into that problem. It also will help you with calculations later on. You understand that what you're looking at is a volume, what you're looking at is a mass. That could really sort of point you in the right direction in terms of calculations. All right. I will skip that one there. All right, so let's talk a little bit about difference about two types of sort of observations that we look at. Qualitative versus quantitative. Qualitative consists of basically general observations about a system. Like, hey, it turned pink, it had bubbles, it had unicorns, I suppose, those type of things. There's really nothing that was measured. It's more sort of just visual observations that you make about a system. Quantitative, on the other hand, does compose of numbers and is basically obtained by measurement. So pretty much all you're going to do today in lab is take measurements, and they're all going to be quantitative. When we take quantitative measurements, we want to make sure that we do take them properly. And that's also a very common problem that people do is they go, well, 52-ish, kind of good, seems scientific-y, all that kind of stuff. But, you do want to make sure you always take the measurement to the proper number of digits. Although it may not seem that you're kind of screwing up your measurement, you're making it really worse than it should be. So it's really, really important. So it's very important in chemistry. We deal with both of these things a lot. A lot of experimental work is quantitative, where we take measurements, we take values. But a lot of, experiments are qualitative in the sense of, you're observing what happens and so forth. If you end up in 1B at some point, they have nothing but labs that are called qualitative analysis, where there's absolutely no calculations, nothing there other than, look, it made a solid. Hey, that would say like a white solid, that's a yellow solid. There's things floating, in the solution. There's really no measurements that you make other than, sort of qualitative observation about what's going on. So let's talk a little bit about, before we go too far, scientific notation. So obviously in chemistry and a lot of sciences, we have a lot of really large numbers. We have a lot of really sort of small numbers. So we do use scientific notation to help us sort of handle those numbers. You may be familiar with scientific notation, but as we will see, it has a general formula of n times 10 to the n, where this number is a number between 1 and 10. And 1 and 10 does not mean 10, does not mean 20, does not mean 100. It is a number between 1 and 10. Yes, sir. 1 digit before the decimal. Okay. So it does need to be written as a number between 1 and 10. And it cannot be 10, it cannot be 20, 100. It can't be less than 1 either. It does need to be a number between 1 and 10. Now, it is times 10 to this little n here. This little n here is either a positive or negative number. And it really depends on sort of which way you have to move the decimal point to get yourself to a number between 1 and 10. So obviously the purpose of this is, if we were trying to do a lot of math, say with the number we see on the screen there, 0.000, I'm tired of saying all those zeros at this point, we're probably going to lose some zeros along the way. So we can use scientific notation to basically help us not lose any numbers, keep track of numbers, make some of the calculations a little bit more manageable. So as I mentioned, it does need to be 1 times, this n is a number between 1 and 10. And again, positive or negative there, depending on which way that you move it. So for example, if I had the creative 1, 2, 3, we would assume that the decimal point is here. If I moved it one place this way, that gives me 12.3, which is not a number between 1 and 10. I do need to go one more place. That gives me 1.23, which is a number between 1 and 10. I moved it 2 decimal places, which means I would be times 10 to the 2. The exponent here would be positive. The easy way to remember that is, if it's sort of a large number, anything sort of above 1, it's going to be a positive exponent, as opposed to if you had 0.123, I would need to go one place to the right here to get me 1.23, and this would be 1.23 times 10 to the minus 1, minus, because really I moved the decimal place to the right. Small numbers should have negative exponents. Questions on that there? So let's take a look at some of these examples and see, how to put these guys into scientific notation and how we get there. There we go. So for example, here, we do want to go one place, 2 places to the left. That gives me this number, which is 5.68762 times 10 to the 2. Here we would want to move the decimal place to the right, 1, 2, 3, 4, 5, 6 places. Again, it's a small number, which means we're going to end up with a negative exponent, as we see here, and we end up with 7.72 times 10 to the minus 6, We have here again, not written, but we assume the decimal points there. So we would go 1, 2, 3, 4 places to the left to get us a number that is between 1 and 10, which would be 1.25 times 10 to the 4. Again, large number, positive exponent. And lastly here, just one place there to the right gives us 1.35 times 10 to the minus 1. Now you may be wondering, why maybe we left off some of these zeros and kept some of all these numbers. And it has to do with, as we'll talk about here in just a second, it has to do with the significant figures. So when you write something in scientific notation, you should never change the number of significant figures. So the reason why, for example, we kept every single number here on this guy was because all those numbers are significant, which means the original number had 6 significant figures. When we wrote it in scientific notation, it still has 6 significant figures, and that's why we kept all those numbers there. Whenever you write a number in scientific notation, all these numbers are significant figures. We're going to talk about what significant figures are here in just a second. But whenever you have a thing written in scientific notation, anything that comes before the times 10 part is considered significant. This number, as we'll talk about, has only 3 significant figures. So when we wrote it in scientific notation here, it had only 3 significant figures, which are the numbers that came before the times 10 part. Any questions on that there? All right, so take a second, write these guys in scientific notation here. All right, so let's take a look. We would assume decimal point would be here. So we'll go 1 place, 2 places, 3 places, 4 places, 5 places, going to get us a number between 1 and 10. This would then be 4.25 times 10. I messed up how many times I counted there. 1, 2, 3, 4, 5, looks like, yeah. Times 10 to the 5th meters. We will talk about it here in just a second, but these zeros are not significant, which is why I left them off. This means that this has 3 significant figures, as we'll talk about here in just a second. That's why we do leave off the zeros here. Here we would want to go the opposite way. 1, 2, 3, 4, 5, 6, and 7 places gives us 8 times 10 to the minus 7. Small number, negative exponent, and this would be grams. Any questions on that? And again, the significant figures here should make sense in just a second, as we will obviously talk about that next. More importantly, though, I think before we sort of move off of significant figures is how to punch the scientific notation in your calculator. So when you do scientific notation, in your calculator, you should always use your exponent button, which is an EE button on most calculators. You should have a EXP button. And some of the newer ones will have like a times 10 to the n type button. And these are the proper ways to punch things into scientific notation. We're going to start with just these guys first, and then we'll talk about what you need to do if you have that button instead. For example, if I wanted to take 1.25 times 10 to the minus 4, and I wanted to divide it by 3.2 times 10 to the 11, the way I would punch this into my calculators is as follows. I would do 1.25, then I would hit my exponent button. So either your EE button or EXP button. And most people's calculators, it will probably either show something like this. It'll put an E. It may show something like it pops up a couple of zeros or something like that. When you hit that EE button, that stands for the times 10 part. of the number when you write it in scientific notation, which means you should not be hitting the multiplication button. You should not be hitting these inverse log buttons, second log, shift log, any of those things. You just hit that. Then we want to put -4. So also important on your calculator, you usually have a negative button that looks like this, or maybe one that looks like this, not the subtract button. You would hit one of those buttons, and then you hit 4, and it will make like a -4. And that is the proper way it would kind of come out on your calculator. You obviously would then hit the divide button, 3.2 exponent button on this guy. We'll put a 3.2 in E. This is a positive, so you just need to hit 11. Looks something like that. Then obviously you hit equals. You want to make sure that you use your exponent button. By the way, if we do this, we can try on this bad calculator and see. Let's see. 1.25 exponent button, negative button, and 4 divided by 3.2 exponent button 11. End up with, like on your calculator, 3.906. Okay, my number is 25 times 10 to the minus 16, which we'll talk about. You probably want to take to something like this, but more importantly, this is what you should sort of be getting. If you find yourself doing calculations and you find yourself like the front part of the number, like this part, looks okay, but the exponent part is off, it is probably the way that you are punching in your calculator scientific notation, and probably you're punching it incorrectly. So no equation you hit the multiplication button, the log button, or anything like that. That is the right way to do it. You want to make sure that you actually do it that way. Any questions on that there? Now, if you happen to have one of the kind of newer ones, if you will, that has this button, so maybe I can do the different color here. Let's see if that'll change the color. Okay, let's say you have this button here. You pretty much need to do the same thing, except that because of the way most of calculators that have that button are programmed, you have to put parentheses around everything. So if you have that button, you've got to put parentheses around each of these numbers. Otherwise, your calculator will do the wrong math. And usually you know if you have that button, because usually your calculator will also have like a little wheel type of thing. And you oftentimes have to use that as well. So if you were going to punch it in with that, you would have to do something like parentheses 1.25. You hit that button. It will do this for you, and you'll find your little cursor up on top. You hit your negative and 4, it will go -4. And problematic is your cursor is still up on top. You need to hit this to bring your cursor back down so you can close the parentheses. So there's a few more steps that you have to do based on the way those calculators are programmed in order to punch it in correctly in scientific notation. If you need help on any of that, all you have to do is ask. Yes, we'll figure it out together. Just bring me your calculator, and we'll make sure you know which one is the proper way to do that. But so again, on your calculator, try the one I put up there. Hopefully, if you got that number, you're probably punching it incorrectly. If you didn't, then at some point, make sure you come bring your calculator up, and we'll make sure that you know how to properly punch it in. Any questions on that? But very, very important in chemistry that you actually use the exponent button. Later on in chapters, we'll be using things like logs and stuff like that. And if you are punching these things in incorrectly, you will find out very quickly you'll be very, very off on your calculations. Any questions on that? Yeah. All right. Now that I wrote all over that screen, like this. I'll just tell you what it says it's about, and then we'll look at the next one. All right, so when we take measurements, there's always some type of uncertainty in the measurement. No matter what measurement that you do, there's always going to be some degree of uncertainty. That degree of uncertainty will be based on the piece of equipment that you're using, as to how much uncertainty there is. So let's take a look at maybe here, and I'll scribble here. So for example, if we had, say, a nail such as what we have here, and we look at the scale here, when we take a reading here, we want to do a couple of things. First off, whenever you take a reading with any type of measuring device, you always want to look at the scale. So here we do see the scale, and we do see that it is in centimeters, and the big units are basically our big divisions are 1 centimeter. Now, when we look between, say, actually we'll come down here, if you will. We look between, say, something like 1 and 2. We have basically 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 markings. There's basically 10 markings between the major units, which are basically these guys right here. There's 10 markings. Now, if the major division is 1 centimeter and there's 10 markings, what does each little marking represent? Each little marking represents 0.1 centimeters, right? So each little marker would represent 0.1 little divisions. So for example, if we blew it up, if that was 1, this would be 1.1, 1.2, 1.3, 1.4, and so forth along the way. If that was 1 and 2 centimeters. So when we take a reading of something like this, there should be certain numbers that no matter who takes a peek at it, everybody should agree with the same numbers. Everybody, if we look at this little nail here, should agree it's past 2. And that is the 5th, 6th, 7th, and I'm getting old to see that, so I'm going to go up there. 1, 2, 3. So 3 markings past that, so that is 8. So no matter who takes a look at it, everybody should agree it is at least 2.8 centimeters. And I think they kind of blew it up here, but right about there, right? 2.8 centimeters. Now the problem is, if we look at it, it's not exactly on the 2.8. It's not exactly on the 2.9. So there's some degree of uncertainty exactly where it is. I may look at it and go, I think it's like kind of halfway between the 2 markings, and I would record 5 and the units as centimeters. And I would record 2.85 centimeters. When we record a measurement, you should always record all of the certain numbers. So all of the certain numbers. Which in this case is the 2.8. Plus, and when you take a measurement such as that, always record all the certain numbers plus that first uncertain number. And that technically is what significant figures are. Which means this measurement that I took of 2.85 has how many significant figures? It has 3 significant figures. The 2.8 is correct, certain. The 5 is the uncertain number. It would have 3 significant figures because of that. Now, somebody else may look at it and go, I think it's like 2.86. I think it's like 2.84. There's usually like a plus or minus sort of deal on the last digit there, plus or minus 1. Any questions on there? So as I mentioned, it is customary to record the first number plus the first uncertain number, and that is our significant figures. There we go. There we go. So for example, if we looked at something, say like this. Probably should do my thing a little bit bigger. All right. So let's say that we had some liquid in a container such as this. Just a little bit Just here. I failed hard. You'll find that out very quickly here. All right. So if we look at this particular scale here, that is 10, that is 20. And when we count from 10 to 20, starting with actually the one past 10, that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 markings. So again, we have 10 markings between 10 and 20 in this case. That means each small marking is how much? Each small marking is, these are milliliters, we'll call it, 1 milliliter. This would be 11. This would be 12. That would be 13, 14, 15, 16, 17, 18, 19, and 20 going all the way up. Now, whenever we take a reading of a liquid in a glass container, there's usually a curvature of the liquid. I'll exaggerate it like that. And that is what is known as the meniscus. We should always take the reading from the bottom of the meniscus. So you should always record from the bottom of the meniscus. And the real reason for that is what is happening and why it curves up is there's a stronger attraction between the glass and the solution. So the sides of it rise up in the actual container, where the actual volume is in the middle there on the bottom is really where it's at. So you'll see this kind of curvature. Sometimes it's easier to see than other times, but you should always try to look for the meniscus. You should always try to read from the bottom of the meniscus. And in this case, if we just draw a really bad straight line across-ish. All right. Everybody that looks at this would agree that it is at least 14. Am I bad drawing here? Not exactly 14, not exactly 15. So maybe it's like 14.9 milliliters. These would be our certain numbers. And this would be our first uncertain number. And that means in this particular case, we would record something like 14.9 milliliters, which means this guy would have how many significant figures? 3 significant figures here. They would all be significant. Where the uncertainty lies here in the last digit. Sometimes people will determine maybe the precision of the piece of equipment that you're using. And you could do that by taking the smallest marking, which is in this case, and divide it by 2, which means we could take it to that. So sometimes you may see this recorded. I personally don't do it very much, but you could sometimes see this requires 14.9 plus or minus 0.5 milliliters or milliliters. And that's sort of the range at which you can record for that. I'm good with just the 14.9, and but you'll sometimes see that. Any questions on that? Obviously, if we go to the one previous, we had 0.1 that we could divide by 2. And if we take, let me get this all, 0.1 divided by 2, gets us 0.05 as sort of our degree of error, if you will. Whatever that was, centimeters, and stuff like that. Any questions on that? So you should always look at the scale. You should always figure out what is the biggest markings, what is the smallest marking, and take it basically all the certain numbers plus the first uncertain number when you do that. That also means that let me get back this way. Let's just say that and let's just say we had something which was like dead on that guy. So if we look at this, again, we have 1 and 2 centimeters. We have 10 markings between the two. So the smallest markings is 0.1 centimeters. Here, if I record it, it is 1.1, 1.2, 1.3, 1.4. It's at. So should I record 1.4 centimeters? Should I record 1.40 centimeters? Should I record 1.40000 centimeters. Is there a difference in how I record this number? The answer is there is a big difference in how you record these numbers, even though they all look like 1.4 to you. First off, way too many zeros. We'll just get rid of that. So let's take a look at these two here. 1.4 would have how many significant figures? They have 2. Which would imply that this is the certain number. This is the uncertain number, right? Which means that our measurement here could be as big as 1.5 or as small as 1.3, which if we look at the sort of scale here, my bad writing, this is 1.5 over here, right here. That's 1.3 right there. It's like nowhere near really 1.3 and 1.5. Ignore my bad scribble underneath it. And that is a lot of error that we just made into our measurement by killing off the zero there, right? We look at this guy would have how many significant figures? It would have 3 significant figures, where these guys would be the certain numbers. This would be the uncertain number. That means that perhaps our measurement really is 1.41, or maybe it's as small as 1.39, which is really what we see here, as this is basically 1.4. That's pretty much where we're at, right? So that's a pretty good measurement. That is what we should do. So even if it falls dead on the number, and you have the ability to go to one more decimal place, you do need to keep the 0, because if you don't keep the 0, you just made this thing a very crappy measurement right there. Yes, it has a lot more error than it should, and you need to keep that 0 to keep really, the measurement correct. Any questions on that there? Okay. So what we also see is, typically speaking, you could take your measurement to one more place than the smallest digit. Here, the smallest digit was 0.1. We could take our reading to the second decimal place. Here, the smallest digit was a whole number. We could take our reading to one more place to the right of the whole number and take it to the first decimal place. Not always works, but it works in most cases. One more place to the right, one place really quick where it might not work. Find somewhere where I didn't maybe scribble all over the place. Let me see here. There we go. So for example, if we had say these were milliliters, that is 10, and there's only now 1, 2, 3, 4, 5 places between 10 and 20. In this case, each one represents actually 2 milliliters in this case, which means this is like 12, this is 14, that's 16, that's 18. Which means if you find yourself like right there between 12 and 14, what goes between 12 and 14 is 13, right? There's not enough room there to figure out where 13 begins and 13 ends and 12 begins and 12 ends in that little space. So in this particular case, be like an exception. You can't really go one more place to the right, but you can only kind of go to the whole number. Question on that? Now, there is a difference between accuracy and precision. When we talk about accuracy, what we're talking about is how close we are to the true value. So if you are very close to the true value, you're very accurate. So if the true value was 5 and you got like 4.99, you're very accurate. Precision, on the other hand, is how close a set of numbers are to itself, to one another, I guess is the way to put that. Precision refers to, a lot of times, how repeatable something is. So for example, if you do a experiment and you do it 3 times and you get like 5, 5.1, 4.9, it was very precise, right? You were able to repeat it very much the same way. If you did an experiment and you got like 5 on the first one, 20 on the second one, and 0.2 on the third one, that was very, very different from each other. All those trials, very bad precision. So precision is how close a set of numbers are to each other. Accuracy is how close you are to the true value of that number. And just to illustrate that, I think we have like the, oops, get it here. Here's some bullseye. So we throw our darts here. The goal here is obviously to get to the bullseye right there in the middle. We can see that these darts are not accurate because we didn't hit the bullseye, and they are not precise, right? They're kind of all over the place. This one even missed, right? Very badly. So this first guy would be inaccurate and imprecise. The second one, we have nice clustering, if you will, of all these darts, which means it is very precise, but not very accurate, right? Again, the goal here is to hit the middle. So you can be precisely not accurate, right? You can be really bad at something and you keep doing it the same way, right? You do it over and over the same way, but you keep doing it wrong the same way. So you can be very precise in that, but not very accurate. Here we got everybody clustered, and we also are right there on the bullseye. That is both precise and accurate in that case. So you can be, again, as you see in the middle slide there, very, very precise, but you can be very off from what the true value should be. Usually, if you're pretty accurate, you probably would be pretty precise in a lot of cases. But that's usually the deal there. Any questions on the difference between those two? All right, so take a sec here and decide which measurement it is here. Hopefully it's the right one. Sometimes the line moves when it goes on PowerPoint, but hopefully it doesn't. Look, so really we're looking between kind of here, which is 2, and this is 3. And again, if we count the dots between them, really starting here, past it, there are 10 dots. And the difference between 2 and 3 is 1 centimeter, which is the big markings. The small markings would then represent 0.1 centimeters, which means this would be 2.1, 2.2, 2.3, 2.4, 2.5, 2.6, and 2.7. So we'll use the arrow there as a guide. So it is at least 2.6. That would be our certain numbers that no matter who takes a look at it should agree. We do have the ability to go one more place over. We also see it's not exactly 2.7, and it's not really close to 2.6. So perhaps 2.69 centimeters here, which would be this guy, would be correct. Again, to get this sort of difference, the smallest marking is 0.1 divided by 2, 0.05 centimeters. Is where that comes from right there. So you take the smallest marking divided by 2. By the way, this would have how many significant figures? It would have 3 significant figures. Again, all the numbers here would be significant. All the certain numbers plus the first uncertain number. Any questions on that one there? All right, try another one here. Take a reading on this one and see what you end up with. Okay, so let's take a look. So same idea. This is 9. That is 10. So that is 1 centimeter difference as our big marking. Again, if we look at this, we got 10 markings, which means each of the smallest markings are 0.1 centimeters. Again, this would be 9.1 here. That would be 9.2 and so forth. Here we see it's just barely over 9. So we definitely know it's not exactly 9, it's just over 9. So 9.0 would be certain, at least. Because this is 0.1, we do have the ability to go a little bit one more place to the right there, which means in this particular case, it's kind of close to the 9. So it looks like they went with probably 2 centimeters in that particular case. And again, here we get our kind of precision by dividing by 2. Get you 0.05 centimeters. So in this case, it looks like C would be the winner there. For measurements for us, to be honest with, in our class, you don't have to give the plus or minus 0.05 unless it specifically asks you to do so. So if this was a question, you could just lay up 9.02 centimeters, and that would be perfectly fine in terms of the answer. This also would have, in this case, 3 significant figures. Not everything has 3. It seems like we had a bunch of them, but Again, this would be 3 significant figures, where again, the uncertainty lies here with the last 2. Again, telling us, it really could be like 9.03 or 9.01, which really, if you look at it, that's pretty much where it's sitting in that ballpark in terms of the error. Again, we would not want to go with just 9.0 centimeters here. If I did that, that would have how many significant figures? 2, where the uncertainty would be here. And again, now you're looking at, maybe like a 7 to 8 or 7 to 10 sort of swing in terms of where they could be. That would not be good. Any questions on properly taking measurements here? All right, so we're going to do experiment 2 today, which is all about properly taking measurements. So we'll start at 12. I'll see you there.